Hi, everyone. Thanks for coming. So I'm Shellie Habel. I am currently working on my PhD as a coastal geologist. I just got a position a couple months ago working with Hawai'i Sea Grant within the state at the DLNR. And I help to make decisions on, or inform decisions on coastal development and what we should do about sea level rise. Yeah, it's a real honor. It's a very interesting position. So my research mainly has to do with making sea level rise related maps, flood maps. And so part of like learning about coastal processes, coastal geology, flood mapping is I got to learn the whole history of what's gone on with the ocean, sea levels. It's gone up and down a whole bunch throughout history. And I get to learn what's going on in the future. And so I'm just going to do like a whirlwind tour through the topic of sea level rise and try to keep it understandable. So when you guys look at the news, when you guys see stories in the news, it's going to make a lot more sense. And you're going to get a sense of how freaked out or not freaked out you should be. Okay? So I'm going to start at the very beginning, a very good place to start, as Mary Poppins always said, and that's with the Google. And so when you Google sea level, what you get is a whole bunch of talk about how it's used as a datum or a reference point from which you measure elevations. So you can measure the elevation of a bridge from sea level, and the driver of the boat can know if there's enough room to pass under it. Or they can use it as a reference for how deep the water is. So they can map that, and they can map a harbor. So they can map a harbor, and boats can know, ship handlers can know whether or not they can end up or drive in certain parts of the harbor without hitting the bottom. And also they use it in aviation. So they measure using an altimeter, which measures pressure, which is calibrated to the pressure that exists at sea level. So this is sea level is a datum, and we've always kind of known it as a datum, something to measure something from. So it kind of makes sense that we are having trouble wrapping our heads around the fact that it could change levels. But it does, right? Sea level changes. It changes every day, right? With the tides. The tides go up and down every day. I'm wearing a watch that tells me when the tide's going to be up, when the tide's going to be down. It's very predictable. And a lot of that, it's super predictable because it's based on gravitational pulls from the sun and from the moon. And so the sun and the moon, they exert gravity and they pull the water towards them, but also there's a bulge on the back end too. So it creates like a football shape of what the ocean is doing. So you have the pull underneath the big body, like the sun or the moon, and then you have that inertial pull at the other end. And so the Earth passes beneath that football shape that, say, the sun is producing. And then the moon goes around the Earth. It takes about a month to go around the Earth. And so its football shape moves around as the moon moves around. And it's when those two football shapes align that you get your highest tides of the month. And it's when they're at right angles to each other that you get the lowest tides of the month. So at spring tides, that's when those two football shapes align. And when they're at 45-degree angles, that's when you get your lowest tides. That's the neap tides. And it gets a little more complicated because the moon's orbit is not circular. It's actually an oval. And the Earth's orbit around the sun is also not a circle. It's elliptical. And so there's this celestial dance that's going on up in the sky that's causing our tides, that's causing the up and down motion. That's very predictable. And we can check it out at the local tide station. You can see here, this is at the local Honolulu tide station. The blue represents the predicted tide, and the red shows the observed. So are they the same? Did we do a good job with predicting those tides? What do you think? okay, but not perfect. So what's going on? Why is it different? Why would it be different than the predicted? Got currents, we've got wind. That's all messing around with this big sloshy ocean. So were you guys around? Oh, I'm having problems with this. Were you guys around last summer? Yeah. For the extreme high tides? You guys remember that? And the tides are about a foot higher than the predicted tide. And that's because winds and currents kind of worked on this big sloshy ocean to produce a big bulge or anomalous sea level that was centered kind of around the islands. And you can check this out on the NASA webpage. They measure the surface of the ocean and put together a map. And you can view the sea surface as it progresses through the year, every month. So these are monthly changes in that bulge. You can watch that bulge wash across the islands. For those sea level anomalies and the tides, they occur on top of an already increasing sea level. So these are levels of the ocean from our tide gauge, and if you draw a straight line through those water levels, you'll see that the water levels are slowly rising at about 1/2 an inch for 10 years, which doesn't seem like much, right? 1/2 an inch every 10 years, that's like almost imperceptible. But it adds up over time. So just as an example, you can see here, there's this point during 1920 that's kind of like a big change in sea level. It's like a big spike that hadn't been experienced in the records before that, in the 20 years before that. But if you draw a line straight through from that anomalous sea level in 1920 onwards, you can see that we're starting to hit those levels more frequently, and we're surpassing them. Okay, so these high tides are getting more frequent and they're getting more extreme. And that's what we can expect as we move forward in time. But okay, this is our tide record. Let's look at Key West, Florida. So their rate of sea level rise is a little bit different. They're experiencing 1 inch per 10 years. Then you have Galveston, Texas, experiencing 2.5 inches per year. That's 10 times the rate that we're seeing. But then you have Juneau, Alaska. You have sea level fall at a rate of 5 inches every 10 years. So what's going on? Does anybody know? Can anyone explain this?
Land is lifting because the glaciers are melting.
Got it. You got it. A+. Right. So yeah, I was going to go through this whole thing, but you totally explained it for me. All right, so there's parts of our globe where the crust is actually going up and parts where it's going down because it's levering, right? You have one part that's going up and it'll lever the other side down. And that's because 20,000 years ago, we had these big ice sheets. That was the last glacial maximum. And so you have these big ice sheets that are weighing down the crust. And as it weighs down the crust adjacent to those areas come up. And the reverse happens. The reverse happens when that ice melts, right? The ice melts and then the land doesn't have all that weight carrying it down. And so it'll start to come up. And then it'll lever the adjacent parts of land down. So that's what we're seeing. It's called isostasy. It's an isostatic rebound. And so up here in places like Alaska, where there are big ice sheets on top of that land, those ice sheets have now melted and that land is rebounding, and you're seeing a relative sea level fall. But all around the United States, you're seeing sea level rise. Especially along the East Coast, we're seeing high rates, and in the Gulf Coast. And I'm not sure researchers have quite figured out why land is going down that fast, but I've heard that it might be because of both pumping of oil and pumping of water. But then there's also eustatic sea level change. So eustatic sea level change is going on top of isostatic change. And eustatic change is a change in volume. It's like having a glass of water and taking a drink. You've changed the volume of water in the glass, or pouring water in. So in this case, the place where water is going to and coming from is the ice sheets. You know, you have those ice sheets expanding, and that causes a sea level fall. And then you have them retreating, and then you have a sea level rise. So over the last 125,000 years, we've seen sea levels that are 20 feet higher than today, and we've also seen them 400 feet lower than today. So you'd think if sea level was 400 feet lower than today, you could get in a little, eustatic sea level.
What kind of data do they use to get this going back thousands of years?
They use, there's these little creatures.
You gotta be a little louder for me.
Okay. Can I answer that in the question and answer portion? Because my talk is like 45 minutes, set. But
think of a good answer.
I have a really good answer. I have a good answer, but it's going to take a while. Okay. All right. So sea level has gone up and down, and if you take an ROV or you take a submersible down to 400 feet, you can find corals that are skeletal corals that are a type of coral that only grow in very shallow water. Right? So you can take a sample and date it, and it's 20,000 years old. And that's one of the bits of evidence that shows us that sea level was down that far. And also, there's the other case where we can find coral up on land. And this is over in Nanakuli. Yeah, so you can actually go inland and find corals up on land. And geologists have gone out and mapped this. It's pretty extensive. You can find all these uplifted corals, or not uplifted, but all these corals up on land in higher elevations because sea level was at that height 125,000 years ago. So there have been a couple of geologists that have gone through and taken records of when they build a building, they have to bore down and make supports for the building. And when they make those supports, they bring up the material and take a look. And geologists have put that all together into a map of the subsurface. And what they've found is that coral extends, these coral benches extend all the way past King Street. So all the way past King Street was once underwater. You can imagine that. There's a bunch of buildings there now, but all of that, like most of our city, Honolulu, was submerged. And have you guys heard of the Maili'ili Caves? So there's these karst caves back by King Street that they were bits of old coral that grew, and then because sea level was at that height, and then sea level subsequently fell, groundwater percolated through there, dissolved the calcium carbonate from the reef material, made caves, and here you have it. There's a whole bunch of caves underneath the city. And this is what happens like in Florida when you see sinkholes and stuff. Those are karst caves. All right, so the thing, okay, so sea level is going up and down a whole bunch because water is getting locked into ice sheets and dispelled from ice sheets, and it's kind of cyclical. And it's because temperatures go up and down through time. And there's two main things that cause temperature change on our planet. That's the amount of sunlight coming in and the amount of sunlight being trapped. And so things that would cause incoming sunlight to change are different ways our planet orbits around the sun. So these three cycles are called Milankovitch cycles, named for one of the guys who figured it out mathematically. So there's one cycle called eccentricity, where the Earth's orbit goes from circular to an oval, and it takes 100,000 years for it to go through that cycle. And And the next one is obliquity, which is the tilt of the planet. So our Earth goes from being tilted towards the North Star to being tilted toward Vega. And it takes 41,000 years for it to go through that cycle. And then there's precession, which the Earth has a wobble, and it takes 23,000 years for it to complete that circle. So if you add all of that up, then that amounts to different amounts of radiation or sunlight, basically different amounts of sunlight reaching our planet. And then there are changes in the amount of sunlight bouncing back out to space, which changes the amount that's being held inside our atmosphere. So there's all sorts of different feedbacks that lead to the amount of sunlight that gets trapped in our atmosphere. So one of the positive feedbacks is temperatures go up, which melts permafrost. Permafrost has greenhouse gases in it, which lead to a higher amount of greenhouse gases in the atmosphere, which traps more sunlight, which makes the temperature go up, which makes more permafrost melt, which makes temperatures go up. And so that's a positive feedback, right? You're getting a feedback loop there. But a negative feedback is when you have greenhouse gases in the atmosphere. Trees take in a lot of those greenhouse gases, like CO2. It takes in CO2. Forests proliferate, taking up more CO2, and that draws greenhouse gases back down. Those are just two examples out of probably millions of examples of positive and negative feedbacks that are affecting how much sunlight is bouncing back out. And so our planet's always kind of in a state of equilibrating. It's always kind of out of whack, right? It's always kind of adjusting to these positive and negative feedbacks that are in process, which are bouncing kind of off each other. It's pretty dynamic stuff. And then you put humans in the mix of an already dynamic system, and we are digging materials out of the earth and vaporizing them. And those are increasing the amount of greenhouse gases we have in our atmosphere. Okay, so already on top of a dynamic system, we're causing a little bit of a wonky flux ourselves. And just to give you a sense of kind of how out of whack our planet is, or the type of out of whack it is right now, I'm going to show you a video from Chasing Ice that shows that our ice is melting. It's adding, there's two things we know. Temperatures are coming up, ice is melting. Actually, three things. And we know that sea level is coming up. And this video just goes to show that the ice melt is extreme.
On the phone with Jim on one of our...
Have you guys ever seen Chasing Ice? No?
Nothing's happened.
It's going well. We had some serious bouts of wind.
So in Chasing Ice, there's a National Geographic photographer he has a team of people who go out with cameras and they take images of ice calving, and they take images through time of ice retreating back. It's on Netflix, so I would highly suggest it. It's a good movie.
Where is this taking place?
This is Greenland, off the west side. Mhm. So these are skyscraper-sized ice chunks that are falling from land into the ocean. It's just like if you pour ice into a glass, that level of water will go up. So whether you're convinced or not that humans are causing temperature rise or ice melt, you can see that the glacier, like there is calving going on. There is ice being added to that sea level, and sea level is going up. You can see it in the tide gauges. So like
Calving face is 300, sometimes 400 feet tall. Pieces of ice were shooting up out of the ocean 600 feet and falling.
Is this sea ice or land ice?
this is land ice. This is land ice falling
The
into
only
the
way
sea.
that you can really try to put it into scale with human reference is if you imagine Manhattan. And all of a sudden, all of those buildings just start to rumble and quake and peel off and just fall over and roll around. This whole massive city just breaking apart in front of your eyes. We're just observers. It's two little dots on the side of the mountain. We watched and recorded the largest witness calving event ever caught on tape.
So how big was this calving event that we just looked at? We'll resort to some illustrations again to give you a sense of scale. It's as if the entire lower tier of Manhattan broke off, except that the thickness, the height of it, is equivalent to buildings that are 2.5 or 3 times higher than they are. It's a magical, miraculous, horrible, scary thing. I don't know that anybody's really seen the miracle and horror of that. It took 100 years for it to retreat 8 miles from 1900 to 2000. From 2000 to 2010, it retreated 9 miles. So in 10 years, it retreated more than it had in the previous 100.
Okay, so yeah, that was a little spot off the western side of Greenland. You can see from this map, these are rates of ice loss from Greenland. So that was just one little speck of what's happening all across Greenland. Just one little speck of the ice sheets, of like the ice sheets on Earth that are experiencing this type of loss. So we can see that ice is getting into the ocean, and we can see that ocean is rising. And so whether or not you want to get into the politics of who's causing it, we still, no matter what, have to attend to the consequences. And so with that, you have to look at different sea level rise projections, what's expected for the future. And this is where it gets kind of complicated. This is where you see, like on the news, 1 meter versus 2 meters versus, like even if you look on here, it goes from 0.3 all the way up to 2.5. So I'm going to break down this slide. It looks really boring, but I think it's one of the most important slides. So I'm going to spend a couple minutes on it. Okay, so on the left side of the little plot at the bottom, you'll see levels of sea level rise. Those are just benchmarks. And they go from 0.3 meters, which is like a foot, all the way up to 2.5 meters. And on as you move to the right, those percentages are probabilities of exceeding those benchmarks. Okay. So as you move to the right, what you're seeing is uncertainty of what we as people will do, because those are they're called representative concentration pathways. So RCP 2.6 represents if we as people started shutting down our use or our burning of fossil fuels, and that CO2 started taking a dive, atmospheric CO2. In addition to that, it includes planting forests and doing things that would suck CO2 and other greenhouse gases out of the atmosphere. So the first one is if we do all that by 2020. So it's a year and a half. You think we're going to hit it? Probably not. Okay, so let's not even worry about that first chunk, because it's probably not going to happen. All right, so let's move to the second column, 2040 emissions. That's if all that stuff happens by 2040. You think that might happen? No? Maybe. I'm hopeful still. All right, and the very last column is if RCP 8.5 is if we do business as usual, same old, which you think that'll happen? Maybe. Hopefully not. And so as we move down the column, that's uncertainty due to ice loss. So researchers like glaciologists can't really wrap their heads around how fast ice is melting from glaciers. And they've tried to use models to model it, and they can't get those models to capture what's actually going on in real life. And so those very extreme scenarios at the bottom, the high and the extreme, those represent if we have catastrophic ice loss faster than we can kind of imagine. So the probabilities are very low. At the very top of that plot, that represents the lowest scenario, 0.3, and that's just if we draw a line, like I showed you the line drawn through the Honolulu tide gauge. That's just drawing a line through the average sea level we're seeing. So that's basically certain. That's why you're seeing the 96% or 98% and the 100%. It's basically because those are certain. So you see the meter a lot in planning, because that is, if you look at the probabilities, there's like 17% probability of exceeding that level. That's like 1 in 5. So if you're going to build a building and there's a 1 in 5 chance, you know, I think that's a pretty high chance still, but it's more conservative than planning for 0.5 meters, in which you see, you know, 73% probability, 96% probability, which is still pretty certain. So all of this basically, like the sea level projections, are based on probabilities. So say you're a planner and you're planning to build a nuclear power plant. Which projection are you going to use in your planning? The extreme one. Yeah, the extreme one, definitely. I'd go with you as a planner. If you're planning, like, I don't know. If you're planning a revetment or something that's supposed to go out into the water, right? Something that's going to be submerged anyway. It's not going to be, it's probably going to cause some wonky effects in the ocean, but it's not going to be a totally big deal if it's overtopped. It's probably okay to use, I don't know, intermediate or lower probabilities. So the different projections that you see are just based on what they're being used for, whether they're being used for something that's a high priority like decision versus a low priority position or decision. Does that all make sense? Because it gets a little bit more complex. Mm-hmm.
What kind of downturn are you talking about? Is that like complete cut out of fossil fuel burning, or? Yeah.
No, not a complete cutout. I think it's just a reduction in the instead of seeing instead of seeing carbon emissions on an uptick, it would actually be on a downtick, which we started to see, I think, a couple of years ago, but then it started upticking again. I'm having trouble with this PowerPoint. It gets a little more complicated, and then I'll stop. I'll go to another subject. Okay. So there's ice sheets, and they have their own gravity. They're massive, and they pull water towards them. And so as they melt, that gravity, it decreases, and water that was pulled towards them sloshes away. And there are researchers that model where that water will go. It's called ice sheet fingerprinting. And you can see that in Honolulu, we get all the fingerprints. Like ice sheets, the amount of melt that we receive from the ice sheets is pretty high when you compare it to other parts of the world. And so while our rate of sea level rise is lower than the average rate of global sea level rise right now, it's expected to accelerate pretty extensively past the last half of this century. And so different places are experiencing different amounts of sea level rise, and they're also experiencing, there's places like along the East Coast that are experiencing damages from flooding currently, like in Tybee Island. This is a road, the only road that goes into a community of 3,000 people, and it hosts a tourism industry, and this road floods a handful of times a year to the extent that they have to close it. And even when they don't close it, people who drive along this road say it's pretty sketchy, even when they don't. And by 2060, it's expected that this road will be flooded 50 times a year. This is Jamaica Bay in New York. Currently floods twice a month, and parents joke that they should give their kids wading boots for Christmas. This is Annapolis, Maryland. They're experiencing 900% more chronic flooding, that's not from rainfall, it's just from tides, than they did in 1960. This is Norfolk, Virginia. And the government, they decided to install rulers by the side of the roadway so drivers would know whether it's too deep to drive their cars. And it's also, Norfolk also hosts the biggest military installation in the world. And the main road in and out of the military installation is expected to flood daily in 20 years. And just a fun fact, they also just built a light rail system with mostly federal dollars at sea level. So researchers have ranked cities by their vulnerability, by their area that's vulnerable to flooding. And if you see, Honolulu is number 23. So right now, we already experience at the highest tides, we see wave overwash, which is eroding areas, undermining areas, and causing damage to infrastructure. And we're also seeing drainage failure, which happens when the level of the ocean is higher than the inlet pipe for the drainage. So you'll actually see water flowing backwards. And that happens. This picture was taken in Ala Moana Mall. So this is a tidally influenced puddle. And actually, if you walk down the sidewalk by the mall, this is a king tide, granted, but like if you pop off the manhole, you can see the level of the ocean in there. It's right there. So when it rains, that water has nowhere to go. And so it just piles up and they have to pump it away. And there's another component of flooding, groundwater inundation. And that you have your groundwater lens. It floats just like a boat on salt water because fresh water is less dense than salt water. And so it'll float just like a boat up as sea level rises. And so that will that floods not only surface infrastructure, but underground infrastructure, like cesspools, any kind of buried electrical if it's not sealed correctly. Yeah, so we have all sorts of underground infrastructure to be concerned about. And if you dig a hole around parts of Honolulu, you'll see that groundwater is really not that far down. So you can envision with a meter of sea level rise, or even half a meter of sea level rise on top of this, just a couple feet, we're going to start to see flooding. So as I told you before, I'm a flood mapper. So I've made maps that show the different components of flooding separated out. So the maps I'm going to show you here represent just coastal flooding. This is the flooding that happens as water washes over the shoreline directly. All right, so the depth in the area increases quite a lot. So say you're, someone in charge of making decisions for the city, you're a planner or something. What do you do about this? What do you do? Anybody?
City planners would just put white out over it.
No, they work hard. Those people work hard. All right, if I were a planner, I might think about putting up a wall. There you go. Slap a seawall on it. Okay, that keeps the water out, right? Good job. Problem solved. But then you start.
Groundwater?
What's that?
What about groundwater?
Oh, I'll get to that. But first, this is drainage flooding. This is the flooding caused by water backing up through our drainage systems. So what do you do about that? And this thing. Well, there's these duckbill valves that you could put on the end of drainage pipes that stop water from coming in from the drainage outlet. And they're being used in places like Florida, New Orleans. So say you put that on the ends of all the outlet pipes, and let's assume that they all work perfectly. Then you have to worry about groundwater. So yeah, this water is just filling in the low-lying areas. So what do you do about that? Anybody? Yeah, that's what I would do. Well, some people have talked about putting in like levees and then pumping the groundwater, but that can cause land subsidence, which causes a relative increase in sea level, right? Because land is subsiding as sea level comes up. But then we have those karst caves that we have to worry about that are all beneath our city that water could flow into. But let's just assume that we fill those up with cement and everything is good and we plug all the holes. So it's all good, right? All plugged up, all the holes are plugged up. And then what if we get a storm that, like the one that affected East Oahu here or the one that affected Kauai? Then you get, you basically get Katrina in New Orleans. You had to pay for the infrastructure to be put in, which is extremely expensive. You're out of money, and now you have all this flood damage. You're basically bankrupting the city. You're bankrupting the islands. So, yeah, same thing happened with New York. So, like you said, build on stilts, right? So this is a concern for Florida, for Miami, Florida, which I think is a great idea, where you have your built-up dunes on one side, and you have your buildings built over the water. So these huge buildings are on, it's kind of like they're on pilings, right? Because you have these big supports that are load-bearing that go into bedrock. So you could just take out the first floor, let ecosystems like marsh ecosystems or coastal ecosystems develop beneath the buildings, and then, you know, you'd have your cake and eat it too. Do you guys think this would work for a place like Waikīkī? No? Why not?
Because they're already built and it would make the change.
But it would take money to put up the seawalls. It would take money to put in all the infrastructure it would take to plug up all those holes and do the pumps. Knock the buildings down. Okay, so there's a quote from a famous philosopher, Harvard philosopher. It goes. Here we go. On every level, the obstacle towards transforming our world is the lack of clarity and imagination to conceive that it could be a reality, that things could be different. So if you just step back out of the box and you think about different methods that maybe we haven't used in the past, maybe it need development, but could potentially work, that maybe we could get ourselves out of this in a way that would improve the aesthetic of these coastal places. Like in Waikīkī, can you imagine yourself like driving around on bridges elevated above these coastal ecosystems? You have like walkways and stuff, boardwalk walkways that go above these systems, and you can look down and see like fish or turtles. Let's also assume that they clean up the alawai. Yeah, it could be pretty cool. Even if you get your extreme sea level rise of 2.5 meters, you could still design the city. You could still change the city in such a way to take advantage of the situation rather than fight it. Because if you fight water, you're going to lose, right? If you wage war with water, you're going to lose. That's a famous Dutch saying. Yeah, forget the mangroves too, because I know those are invasive.
Of course, you have a beach lift, right?
Well, you can always take sand from offshore and build a dune inland that could exist like below, beneath the buildings. The alawai, I think that they should, they're planning to turn it back into like a huge golf course, but it might be better to reestablish the wetland ecosystem there and let that kind of clean up the area naturally. We could help the cleanup, but that could.
There was a dictionary years ago in Hawaii.
Yeah.
This was floating cities.
Okay.
On paper. Japan is trying.
Right.
And it's a possibility it could work here too.
Yeah. Even in Seattle, right?
From your floating city, watch all these high rises.
Or you could do both.
Kind of makes a carbon tax look a little bit cheaper.
Makes the carbon tax look cheaper. If you don't think too far out of the box, you can still use things that they install today, like along the East Coast, where they're already experiencing chronic flooding, where they have dry proofing, where you can install, like during the high tide, you can install these little plates that keep water out temporarily. And then as the tide goes down, then you can take them out. They're like little deployables. And I think they're installing them, because of Sandy, they're installing them all along the inlets for the New York subway. Then you have dry proofing, where below a certain flood datum, you can waterproof those floors, and then human occupation could go on floors above. Or you could elevate on fill, elevate on piles, or do floating structures, like you said. I don't know if you guys noticed, but down in the lower left-hand corner, that's Mapuna Puna. And before there were storage units there, that used to be an auto body shop that flooded constantly. And so finally they got out of there. And when they put in the storage units, they elevated on fill. And so now kind of the problem is solved for the storage units for now. You still get like wet tires going to and from that place, but they've adapted to sea level rise, basically. And then after Katrina, they designed a type of home that was amphibious, where you have these beams and it goes up and down. As you have your flood come in, the house floats right up. So your local government is thinking a lot about this. They just the state just put out a report on sea level rise that included flood maps, damage calculations, where they thought about infrastructure, cost of roadways, damaged real estate. Then they've come up with recommendations, mostly for policy, where they recommend changing the zoning, changing construction requirements. And there have already been laws passed based on this report. And it just went out, and laws have already come through, where the law that went through was for environmental assessments, where now in those assessments, contractors have to talk about how they expect sea level rise to affect the project in the future and how they plan to adapt to that amount of sea level rise. Okay, so while this is a pretty picture, I know that the thought of sea level rise is not. Okay, so we have a lot of work ahead of us. Until the day we die, we're going to be working on this problem because there's lots of sea level rise built into the system already. We're basically not going to see it fall. I've heard it said that sea level rise is like aging. You can't stop it from happening. You can prepare for it either gracefully or not gracefully. Okay, and with that, I'll take any questions that you might have, including yours about changes in sea level. You studied sea level.
Gained any knowledge from the Dutch and the Netherlands? They've been managing water for hundreds of years.
Yeah, a lot of their engineers are coming over and helping, especially, I know with Hurricane Sandy, there was a guy, Hank Ovink, who is like a world-renowned engineer that deals with this stuff. So yeah, there are Dutch engineers coming over. They've been really helpful.
What were the dates on the predictions that we had? The data, you know when that was recorded?
Which one?
The predictions for if we managed to get a carbon downturn by 2020.
Yeah.
Do you know when those were collected?
When those were put together?
Yeah.
I think those were put together as part of the Intergovernmental Panel on Climate Change report that they put out in, I think it was 2013. I'm going to say. That's my best guess.
I think that's a great new law we have recently passed about the large buildings having to consider and report how they will adapt to it. Is the same true for residential housing? Do builders of new residential housing or people selling homes have to disclose bring a new flood map?
It's not law yet, but I think the government is working on policy for that. But I think there's some real estate agents who now can cite the report that the state put out. And so yeah, that's helpful. Yeah, it's getting there.